5 minutes late, not that bad. Okay, so the past few lectures, we spent a lot of time learning different tools, looking at memory, a bunch of low-level stuff. So today we're going to take a... So yeah, we went through a bunch of low-level stuff. We looked at debuggers, programs like disassemblers and whatnot. So today we're going to take a step back from all that, and we're just going to read some C code and use a text editor. Just the basics. Just some notices. Project 1 is due very soon, next Tuesday, I believe. And homework 2, it has actually not been assigned yet, but we will probably be assigning something
tonight or tomorrow morning.
Yes. And for that, you will also have time until like next Thursday. So I guess it's not really very soon, but just make sure you don't fall behind on that. Okay, moving on. Today's content, we're going to cover quite a few things. We're not going to go in depth into any of them. We don't care about how to exploit them yet. We just want to see how do these vulnerabilities look, how do these occur. Some of the things we'll talk about, undefined behavior in general, buffer overflows, format string vulnerabilities, how C handles types and some vulnerabilities that may occur by that. We're going to look at some like auditing techniques, why companies don't usually care about security, and we're going to find a 0 day. Okay, starting with undefined behavior. It's often used to describe buggy C or C++ code, or other languages as well, I assume. Basically, it's code that you can say for sure what it's going to do based on the language's implementation. So this can result in unspecified results such as crashes or values being set to stuff they shouldn't be. And yes, can potentially lead to exploitable vulnerabilities, which we might care about as security researchers. Moving on, buffer overflows. Who here has heard of buffer overflows or encountered it in one of their projects? Okay, that's a lot. That's good. So we're talking specific. We're not talking about the stack overflows where you recursively call a function 200 times and you run out of stack space. That's not what we're talking about here, even though that's also a bug, but that one is generally not exploitable. What we care about is our buffer overflows that overflow a buffer. So let's look at this small example here. It has actually 2 small examples in it. So in the first example, it allocates character array called buff1, size 0x20, so 32 bytes, and then it calls gets on it. Anyone know what gets does?
Reads input from standard in.
Exactly. And the issue with gets is there's no way to tell it how much input to read it. So there's pretty much not a single way to use gets securely. So if you take away anything from this, never use gets ever.
I think it prints a compiler warning if you try to use
yes,
it. Yes, don't ever do this. Please stop.
And if you program on Windows, it's never even going to compile. But yeah, Linux lets you do pretty much whatever you want. It might give you a warning, but
I think they actually have to for standard reasons.
So you call gets on it. If the user is nice, he might just give you, let's say this is like supposed to be age. So you expect the user to just enter a number, maybe 3-character range. So you allocate 32 bytes, which is a lot more than you would need, but you just want to be extra safe, I guess. But what if the user's feeling funny and tells you he is 208 characters old? So then suddenly, the buffer can only hold 0x20 bytes. And in this case, the buffer is allocated on the stacks. So you start writing outside of the bounds of the buffer and overwrite arbitrary regions in memory. This is very exploitable, probably the most relevant bug in computer history. Still exists, has existed 50 years ago. So we're not going to talk much about how it's exploitable today. This is going to be in Stephen's next lecture, how to actually exploit it. So we're just going to talk about like how the vulnerability might occur in C code. For example, here, easiest example, calling gets on any form of buffer. Here, this one is a little less obvious. Here it uses the fgets function to read into buffer2 from standard input and the size of buffer2. So here, size of buffer2 means that only 0x20 bytes are read into buff2, which is valid in this case. And then a string copy is performed. So notice here that the fgets, there's So string copy, it basically copies over bytes from one source to the other until null byte is met, which is how C terminates its strings. So here you would expect character 20 can hold 0x20 bytes, character 3 or buff 3 can hold 0x20 bytes. So this copy should work without issues, right? They're the same size. The f get 0 was completely safe. But what's wrong with the string copy? For example, here, if you don't give a null byte, if you just send it 0x20 bytes, then there is no null byte, and the string copy can, for example, copy over extra bytes. If that makes sense. You didn't call with scanf with like %s flag or anything. It's just pure fgets call. The string is never null terminated, or the character array, I guess. It doesn't even have to be a string. So this string copy can cause issues. Yeah, basically anything where more memory can like go into a buffer than it can hold is a very real possibility for exploitation. Any questions on this? Yeah.
What is the value of size of buff 2? Is it like 0x20 in this case, or is it the memory allocation of the pointer buff 2?
It's 0x20. This is actually determined at compile time. The size of macro is expanded into a number as well. Yeah, the size of like this fgets call is 100% safe. There's no issue with this. This is how you should read in buffers. You should probably error check, which is not going to happen in any of these examples for simplicity's sake, but it is a good way to read in buffers. The issue is that string copy in general, you'd probably want to use string n copy to specify an amount of bytes, just to be extra safe. And you want to be sure that it's null terminated if you do not specify a size. Yes?
Does fgets not null terminate the input?
No.
I think, no, fgets does.
No, it doesn't.
On an input, max input?
By implementation, it doesn't have to, I'm pretty sure.
Wait, what?
I look at the docs, it says it doesn't have to. It's up to implementation. Most cases it does not include. That is why the lab was so annoying to write, because I had to manually null terminate every component. They like dealt with the lines.
A terminating null byte is stored in the last directory buffer.
I'll have to double check that, but I'm pretty sure it doesn't
It
have
is
that.
not always. The lab, I was running a lab and I had that issue.
Let's just say for sake of example, even if it did, I'm pretty sure it doesn't, but you may be right. I'm not 100% sure on this.
I was just checking the man page.
Yeah.
So I don't know.
Yeah, that's fine. But even then, like the main takeaway from this, not like about the fgets call, just in general, when you do string copy, you need to be 100% sure that there is a null byte there to terminate. Otherwise, you run into issues. Anything else? Okay, let's move on to the next slide then. Format string vulnerabilities. These are another vulnerability class that's fairly common, very old. Occurs a lot less recently, but it definitely still exists, as I will showcase at the end of class, in very real projects as well. So what are format string? So this is another category that we will be teaching you how to exploit later in the course. So you know how printf functions, for example, you can specify format string specifiers such as %s to print out a string or %d to print out an integer. So what if you just take a buffer that has potentially user-controlled inputs, such as here, you read into the buffer using fgets, and then you print out this buffer. So in this case, you didn't specify any format string specifiers. But what if the user in his buffer puts format string specifiers? Printf, for example, for so the first example here is %p. What if the user provides this as input? So %p space %d space %s space and %x. So in this case, printf would treat these as the first argument to printf, usually which can be format string specifiers. So the %p, for example, would read out a pointer that's stored on the stack. At this point, %d would print out a decimal that's stored on the stack, which in this case would be a 0. %s in this case didn't do anything because there was probably not a valid pointer on the stack, so it couldn't be reference a pointer and print out a string. And %x once again prints out a number from the stack and hexadecimal. So why is this important? Why is being able to leak information that relevant? First of all, the main reason is just it can be used to leak out passwords and various data that shouldn't be accessible if it is stored on the stack, which is a valid way to use it. Another one that is probably more relevant to us is mitigations. So people don't like exploits. So they've written mitigations that the operating system uses to make exploits harder to write. We're going to talk more about them later, just a very quick overview of one. It's called ASLR. It randomizes the address space. So a function would not always be loaded at the same address, but it is randomized. Same as like functions that you call in from libc, or memory on the heap, or memory on the stack. All these addresses are random, and or not completely random, we'll talk more about it later, but they're randomized to an extent. So what does this mean? With this, we can potentially leak out values from the stack that let us calculate other offsets from like various things, and thus bypass these protections. Yes?
So in this example, like I know there's these printf, usually like passing values, but where are the values coming from?
These values?
Yeah.
So when you call printf, the first argument, when you specify more arguments to printf, these are on this stack prior to the printf call. So in this case, it just prints out, or it just uses %p, %d, whatever on the next values on the stack preceding the at the printf call location. So you basically just leak out arbitrary values off the stack.
This is a lecture in like 2 weeks, it's just this one
Yeah.
topic. So we'll go more into it later.
Yeah, so the vulnerabilities pretty much is if you take in a buffer and print it out directly instead of, for example, here you would probably want to like put quotation marks, add a %s, and print out the buffer that way. Then the vulnerability is gone. Very easy to not do, still happened a lot, especially in the past. This can not only be used to leak out values, it can also be used to overwrite values from memory with the %n specifier. We're not going to talk about that right now because that's going to take a while, but it's a very, very powerful bug. Honestly, one of the most powerful bugs there are. Yeah, any questions?
To interrupt before you go on, can you share your screen on Zoom? Sorry.
Yes. The slides are also all up on Moodle.
Something I think was last year, the two bugs we just covered, buffer overflows and format strings, I think were not necessarily for C code, like buffer overflows in general, were 50% of exploits in Migra's database last year.
Buffer overflows?
Yeah.
Yeah, very, very, very major.
Buffer overflows are 50%.
Nowadays, a lot more is like web-based stuff, but
It's a lot of.
yeah. But buffer overflows, like in terms of memory corruption vulnerabilities, buffer overflows is by far the highest. Yeah. Okay, before we move on, any questions about format strings or buffer overflows? Okay. Let's take a step back from vulnerabilities real quick, because the different variant types in C, integers, floating point numbers, whatever, they all have their own vulnerability classes. So let's talk a bit about how C uses different types. Some of the main types would be character types. There's different ones, can be signed, unsigned. Are all of you aware what signed versus unsigned means? Okay, we're going to talk a bit more about that in 1 or 2 slides, but so different character types, they're guaranteed to take up 1 byte of storage. 1 byte of storage does not have to be 8 bits though, but for all intents and purposes, you'll pretty much always see it as 8 bits. And the size of car is always going to return 1. The integer types, there are 4 main ones. Short integers, normal int, or just integers, long int, and long int. Each of these also has a corresponding unsigned type that takes up the exact same amount of storage. Signed integer types are used to represent both positive and negative values, unsigned just for positive values. Floating types, we're not really going to talk about them much here because you don't usually see them much in C programs, for the most part at least. Maybe those are float double and long double. We're not going to talk about them anymore now. And they're bit fields, which you may or may not have seen. You can basically just specify a variable and ask how many bits you want, so you can like create bitmaps and stuff using this type of syntax. Yeah. Okay, so let's talk about unsigned versus signed a bit. Binary encoding. So for unsigned integers, they're in the pure binary form, as you all know it. As is shown there in the example, probably just take a look at that. That can explain it better than I could. Basically just represents the numbers as powers, or the numbers are set up in bits as powers of 2. Then there's the binary encoding for signed numbers that is a little different. In this case, I hope you've all heard of 2's complement in CS230. It's a bit weird, but the sign bit is stored in the, there are a few ones, I mean like the sign bit, 1's complement, 2's complement. Sign bit is very straightforward. You just store a sign bit in the first bit of every integer. 1's complement, similar, is a bit different, and 2's complement is one we care about because that is usually used 99% of the time, pretty much every time. Where the sign bit is 1 if the number is negative and 0 if it's positive. And positive numbers can be just read directly from the number like this. And for negative values, the entire number needs to be negated and 1 is added. Yeah, it's a bit weird doing it in my head. I probably would just write a test program for that if I need to figure it out, or use an online calculator, but that is how they are done. I don't need to really remember that for the most part, but just be aware of the difference. Okay, so we talked about like for example, like some values can have different sizes. These are like what you can generally expect. This is not universally true, but that's the most common implementations nowadays. There are no padding bits in any integer types. 2 complement is used for every signed value. Bytes are 8 bits long. Little endian or big endian are the 2 ones that are usually used. Character types are 1 byte, signed by default usually. Short type is 2 bytes, int is 4 bytes, long is 4 bytes, long is 8 bytes, and pointers depend entirely on system, 8 bytes on 64 or 4 bytes on 32-bit. A lot of these are variable and can depend depending on the system, but these are just what you can generally expect while reviewing code. Just a very small thing about like the maximum minimum values of depending on the size. Don't remember them, but maybe have like a general idea of how big they can get, so you can like do some simple arithmetic in your head about them if an issue could occur there. And okay, so that's what we have on the types so far. Just basic information, but any questions?
Yeah, just a quick question. So with the 2-side thing, basically what you're saying is that like the max value is used as a negative or a positive indicator, which is why it's like in 8-bit it's half the size of the values.
Yes, there is a bit more to it. It's not just the first bit indicating positive or negative, at least for 2's complement. It's a bit more complex, but honestly, just look it up. It's hard to explain, and 230 covered it, so I don't want to go too deep into that right now, but yeah, for the most part, that kind of sums it up, I guess. Yeah.
Oh wait, me?
Yeah.
Okay. In what instance is byte not 8-bit? What else would it be?
Just some very custom implementations that some people may have made. You can always expect to be 8 bits on anything you use, pretty much. That was, I don't know. It doesn't have to be 8 bits, but it pretty much always is.
I just saw a post on Hacker News or something. Somebody built a 9-bit robot.
Yeah.
I didn't even read the
There you
article.
go.
I was like, why? So it's possible.
Yeah.
Can you just explain what you mean by there's no padding in integer types?
So, you know, we talked about that earlier, that like sometimes on the stack, you need everything to be 16 by the line, so you add extra values to the stack. These padding bits cannot exist inside of integer types or any of these types. They can exist, for example, in structures, which may be very obvious, but yeah. Okay. So that's done on types. Let's start talking about some vulnerabilities that can occur from this, starting with integer over and underflows. I assume most of you have heard of this bug. It's basically when you look at the previous table, the maximum, say we have an 8-bit signed value. It can go up to 127. So what happens if you add 1 to it? Well, it can't represent 128. So if you go 127 plus 1 in an 8-bit signed integer, it's going to wrap around and equal minus 128. This in itself is often not exploitable, but this can lead to very serious bugs that, like, for example, pass security checks that it wouldn't otherwise. The same also goes for unsigned values. For example, if you have an unsigned 8-bit size 255, add 1 to it, suddenly it's 0 instead of 256. The same also applies for all other types in here. So that's integer overflows, integer underflows, pretty much the exact same concept. You subtract 1 from this, it suddenly becomes this, the same for unsigned values. So one example, probably the most notorious one, is the Ariane 5 rocket, which self-destructed 37 seconds after launch due to an integer overflow, which, yeah, it caused some damage. Wasn't an expensive mistake. Let's look at an example. So yeah, they can't usually be exploited on their own. They need some extra conditions, but they can often lead to exploits, which we're going to look at one later if we have time. Linux kernel exploit that was found this January, so last month. So when looking for these types of issues in software, you want to specifically pay attention to where integers are added together, subtracted, or multiplied with each other. The same applies for like bit shifts that may multiply an integer that can also very easily overflow. And yeah, so let's look at this example. First one, we declare an unsigned integer a. It's equal to 1. We subtract 1 from it. We set it to 0. We subtract 1 from it. And suddenly it goes from being equal to 0 to being equal to this very large number. Similar with int b. We declare it as a very large number. We add 1 to it. And suddenly it's a very large negative number instead of a very large positive number. This could easily cause some issues. And it's actually oftentimes very hard to get right. So these issues occur a lot. Probably one of the most common vulnerabilities that people find. Yeah. Let's look at a real-world vulnerability. This one's quite old. It's in OpenSSH, which is an SSH server, which is used to get remote access to some form of computer. In this case, it led to an arbitrary code execution, which attackers could use to get onto any system using this bug. So it was a pretty impactful bug. So let's see, what's wrong here? So we allocate an unsigned integer, nresp, some stuff's done that we're just going to happily ignore. Then nresp is set to this function. We're going to assume that the package get-in function is user control. Or maybe not entirely user control, but it can return any arbitrary input. So here, what if this function returns a negative value? Was that the bug? Oh, no, it wasn't. What if this function returns a relatively large value? It's going to pass this check because it's bigger than 0. And here in the here's a malloc call. It's using xmalloc instead of malloc, which is a different implementation. Basically, allocates heap space. So here, it multiplies nresp with the size of a character pointer. And this, since it's a character pointer and not a character, this is not only 1 byte. So this, if this, let's say, is a value that's bigger or is large enough, this will cause an overflow and could thus lead to a very small value. So let's say you set nresp to something where this multiplication leads to a value that's, let's say, 2 over the unsigned integer barrier, so it becomes then suddenly you're allocating or you make an allocation for 1 byte. So what would happen here? You think you can happily do this copy until size nresp, but nresp is still a very large value. However, the response is only a very small allocation, so you have a huge buffer overflow. This time on the heap, not the stack. But yeah, this was actually a real-world vulnerability. I'm not sure when exactly it was found, but it was a very critical one at the time. Yes?
I'm just a little unclear. So where did we cause the buffer overflow? Because nresp, the value of nresp is a huge number, right?
Yes.
And then nresp times the size of car star. Is that where?
That's not where the buffer overflow occurs, but that's where the bug is. nresp times size of character, it can let's say nresp is big enough that let's say this is 2 and this would be 1 over, or it would be the half of unsigned integer plus 1. So you multiply it by 2, and suddenly it overflows and is equal to 1 instead of this very large number. At least like for the duration of this malloc call. And then this malloc call only returns a very small memory region. And then here you still copy this very large amount of bytes over, and you have an overflow.
Oh, thank you.
Any other questions?
So basically, packet get int is a value sent over the network by the person sort of hacking it.
I'm not sure what it was in this context. It may also be set by some other variables in the system, but it is something that the attacker could influence in some ways.
It was, this is the OpenSSH one, right?
Yes.
Yeah, this was, so instead of, it was like public private key encryption. So the server would send you a challenge and you have to send your response. And if your response is valid, then you can log in. But it would just, because your response depended on what your keys were, when checking it, they kind of had to be arbitrary with whatever you could send. So like this.
I see.
Which basically means you could log into any computer with anything at the time.
Okay.
So, just another question. So, what is nrest times like size of car point return? Like, is it going to return like an unsigned integer, or what's it going to return?
It will. This multiplication will basically be changed to whatever type xmalloc is expecting here. So let's say if the xmalloc interpretation wants an unsigned integer, then it's going to be an unsigned integer. It's basically like C, just going to change the type to make it fit in this case. Yes.
So when you set response I to a location that's bigger than what malloc gave it, C doesn't do anything about it?
Nope, C doesn't care.
Okay, cool.
Yes.
Unless I'm not understanding, wouldn't like even if like response like overflow into like a very small number, wouldn't like the memory still be allocated for nrest times the size of car?
Yeah, but that's
Character
only
pointer?
2. Due to the overflow, that size is only like 1 or 2. And then you allocate a buffer of size 1, and then you send 20,000 bytes into it.
It's like getting a high score in like a video game. If you hit the max counter for the high score, it goes back to 0, and you suddenly have a low score.
No, but what I'm trying to get is like, wasn't the malloc done to like this very large number, so like a large? Okay.
Here, it causes this integer overflow. So this number is suddenly very, very small in the context of this call. This nrest.
Oh, that is done before the malloc. So.
Yeah, this is like the size that malloc operates on in this case.
I don't need to put the cart before the horse, but how do you fix this?
There are multiple ways. The main one is you want to check that nrest is not of the size that could cause this overflow. That's like the easiest one. It has performance implications. There are also some weird bit shift magics you can do to stop it, but that gets very complex very quickly. A common one, for example, that's like a very popular example that like a Microsoft senior engineer wrote like an entire blog post on is how to get the average of 2 numbers. But yeah. Okay, let's move on. Type conversions. C lets you convert types as you wish. For example, here you have like some weird example. So here you can, for example, change an unsigned car to long in to a car pointer, whatever. You can do whatever you want in C, and it's not going to stop you. So there are 2 ways of type conversions. Either you can cast it manually, or there are explicit type conversions, which explicit type conversions where you can request them manually, so you put like int before the variable and cast it to an integer, or implicit ones where the compiler does it for you. For example, the previous xmalloc call, if xmalloc wanted an integer, it would change the arguments to an integer to fit that call. Similar to when you're doing int a and long b, and then you're comparing them to each other, one of them needs to be converted to the other's type to make this comparison. The rules of type conversions can be very subtle and can lead to hard to spot bugs. There are 2 main types here listed. Value preserving conversions. So if it goes from a smaller type to a larger type, for example, from a character to an integer, integer has enough bytes to represent anything a character could represent, so nothing is lost there. Or value changing conversions, for example, from an integer to an unsigned integer, where you suddenly, a negative value can suddenly become a very large unsigned value, so it's value changing. Continuing with this, we're going to talk about widening from a shorter number to, or from shorter type to a bigger type. This example from short to an int, for example. The bit pattern from the smaller type are then copied over to the larger type. then it's either 0 extended or sign extended, depending on if it's unsigned or signed. 0 extension basically just propagates 0 to all the high bits, while sign extension propagates the signed bit to all the higher bits. So here's some examples. So for example, an unsigned character to an integer, the value just becomes 5, and it just adds 3 null bytes to the beginning. It's sign 0 extended, completely fine. Nothing can happen. Nothing weird's happening here. From a signed character to an integer, the value is still maintained. In this case, it's going to sign extend because it's a signed value. So since it's negative, it's just going to add a bunch of FFFs to the beginning. Still pretty expected, but it could surprise people if they're not aware of the interaction between like sign extension. And the final one, that's a bit of a weirder one. So you have a character to an unsigned integer, so you're making it larger, and you're changing the type from signed to unsigned. Character is at -5. After this conversion, since this is sign extended, this is filled with FFFs. This is an unsigned integer, so it's not going to treat it as a negative value, so suddenly you have a very large positive number from this sign conversion, similar to how integer overflows or underflows might occur.
Maybe, if you don't mind, one thing to say here is like the word car here means a byte. It doesn't mean a character. If that's confusing, like what character is -5? It's because there is none. It's just a 1 byte value.
Yep.
When you do unsigned int, wouldn't it extend with zeros? So when you are converting character to unsigned,
It extends based on the previous type. So this type was the signed character, since it's -5, so it extends based on that type and fills it with FFFs. Okay. So then there's narrowing, which is a larger type to a smaller type, for example, int to short. In this case, information is basically always lost because you just don't have enough bits to properly represent it. The first example here, from int to an unsigned short, the integer is a very large negative value, unsigned short is positive. Basically just truncate it and cut off the first 2 bytes, and the value just completely changes, not even resembles the initial one. It's integer to a signed character. In this case, you actually preserve the value. You just get rid of a bunch of FFFs, and it still works for the most part. Narrowing conversions you generally want to avoid because they cause weird behavior that people don't usually expect at all. Okay, I think this is the final slide on type conversions. Integer promotions. So if an integer type is narrower than int, it is promoted to an integer for certain operations. Some examples of these types are character short and unsigned character shorts. Whenever these are used in any operation, even if you're just comparing 2 characters, these characters are both going to be promoted to integers. So some example operations that do this would be plus, minus, shifts, whatever. So there are 2 examples. So let's look at this first example here. So in this case, you're adding these 2 together and then checking if it's bigger than 300. So what have we learned? Character, unsigned type, max can hold is 255. So adding these 2 together from what we've talked about so far should cause an overflow, result in a very small number, and thus not pass this check. In reality, however, in here they're both implicitly casted to integers, which are 4 bytes in size. So temporarily, this can hold a larger value, and it actually passes this check and calls the function. Yes?
So would the promotion only be valid for the scope of that
Yes.
if condition?
Yes. That's only for the result of this addition here. Let's look at the example on the other side. Here we said unsigned. So here's pretty much the exact, very similar behavior. So we declare unsigned short A. We would expect it to underflow because the minimum value for unsigned shorts is 0. It is, however, promoted to an integer, and there's no underflow. It can lead to some very weird behavior. And finally, in this case, the function is not called because we said we declare an unsigned value. Yeah, so here the function is called, here it is not, even though this, it looks like it would do the exact same. Just in this case, A is assigned to the result of this. In this case, it's done within this bracket. So in this case, this does actually cause the underflow. And yeah, so if you look at these quickly, these look like they do the exact same. But just due to these integer promotions, they can lead to different behavior. And this is the stuff that results in so many C bugs every single year, or C++. And no one knows this stuff, and everyone makes these mistakes, so they're just so easy to make. Any questions on type conversions? Yes?
Does it always promote to a signed integer?
Yes, I believe so. Okay. Yeah, here are just some examples. We don't have to go through them right now. Just if you want, the slides are there. It just shows how like some type conversions may look. Okay, let's look at some more code examples.
Can you make the font?
Yes.
So I'm gonna turn up the prominence.
Okay. So let's look at this. Very straightforward example. Okay. I guess I have the answer on there, so I can't ask you guys to try and find it. But so here the length is signed, which is if a variable is called length and it's signed, you want to probably double check because length should usually not be a negative value anyways. But okay, let's look at this. So there's length is assigned as a signed value, and then it gets user length from a function. What if get user length, and then it checks if it's bigger than 1024. If it is, it cancels. Otherwise, it reads that length into the buffer. So what if get user length just returns a negative value? Well, suddenly length is a very small value. And this just walks right past this check. But read, it doesn't operate on negative values. Like you can't read -5 bytes. So read is going to implicitly convert this length to an unsigned value, and suddenly you're reading in millions of bytes.
That's crazy.
Very straightforward bug, easy to make. Usually not that easy, but yeah. Any questions on this?
So would you get a compiler warning at least?
No.
But wouldn't the function header for read say unsigned only, and you're passing an assigned value? The compiler could
You can't tell context.
Otherwise, you would have
you declared it as an integer, so it'll assume it's positive.
Otherwise, you would have like errors or warnings whenever you called fgets with an integer, which you wouldn't want as a C coder because you'd have like explicit, which would be a good thing possibly. It would also make the code very messy because it would add like a lot of explicit casts, which would also lead to bugs in that sense.
You could throw a warning at least, right? That could be
Yeah, but
ignored.
that would lead to very, very many warnings. So the way C is
This is
used.
why you use Rust.
Yep. Okay, another.
Hello, Rust evangelism strike force.
Another example here. This is actually a real-world example, a bit more complex. We're going to ignore most of this. This was an Apache bug. I believe this one did not actually lead to remote code execution. It was just a bug that you could use to crash Apache servers. So the bug occurs here. So you read bytes is declared as an unsigned integer, and you read in this function returns an amount of bytes. And here is a check that checks if read bytes is smaller than 0. Well, read bytes was declared as an unsigned integer, so it is not possible for read bytes to be smaller than 0. It is, however, possible for read bytes to be a very large number, which is completely ignored here, and that leads to buffer overflow once again. I'm not going to go too deep into this because the code is a bit more complex, but very similar issue, this time real world. Okay, pointer arithmetic. Small vulnerability, can occur easily though. So pointers can be freely converted between sizes using casts, and operations on pointers are always done relative to the size of the pointer target. So let's look at the first example here. You're declaring a short pointer. Shorts are 2 bytes usually, and then we're setting j to this value. And we're setting j to a point as a pointer to an arbitrary to 0x1234. This is not how you should use pointers. In this case, we just assign j to the address 0x1234, which is completely worthless. Just for argument's sake, this example now. Now we add 1 to j, and now you would maybe think that j would just be the previous value plus 1. However, since it's a pointer of size 2, it added 2 to it instead. So let's look at the other example that actually leads to a vulnerability in this sense. You declare a buffer. You set a pointer to the beginning of the buffer. And then while the buffer, or while b is smaller than the buffer plus size of buff, you read in values into b. So you have 1024 bytes to read into, but this size of buff, or this size of buff is 1024, but this, or I guess this 1024 times 4 because it's an integer. But this plus here, since it's an integer pointer, it's also going to add 4 to buff for every iteration, which leads to an overflow once again. Any
You're saying buff, not b, but buff is a pointer because you've declared an array.
B is a pointer to buff.
So you're saying because you have a pointer on the left side of the less than sign?
Pretty much just because of this addition here. Because so this should move on until 4096, which is 1024 times 4. So each of these increments adds 4 to it, so this should work in theory. But since this addition always adds 4 bytes to buff, because it's a pointer, this is going to lead to a buff. Because instead going to try reading at around 16,000 bytes.
Okay, so it's that buff is actually a pointer rather than a...
Yes, just like pointer arithmetic being adding extra bytes depending on the size of the pointer. Any questions on that? Yes?
Yeah, but this program actually works properly.
This?
No, on the right.
No. This leads to buffer overflow.
But like inside the while, it's B++. And B is also integer.
B++ also going to add 4 to it. Because the pointer size is an integer pointer, so this plus plus is going to add 4 to B on every plus plus. Whenever you're adding to a pointer, you add the size of the pointer to it if you do +1.
Yeah, but like inside the while loop, the pointer
Yes.
adds 4 bytes. And in the condition, it also
So
checks
this
for-
size of buff, it translates to 4096.
Yeah.
So here you're doing buff plus 4096. But 4096 is the amount of, so you're doing 4096 times 4 pretty much, because each of these additions is multiplied by 4 since it's an integer pointer.
So what would be a correct way to write this?
Basically any other way of
Okay.
just not doing this type of weird program. There are a lot of ways to like properly read into a buffer, like mem copy, string copy, whatever you want to do. Or, yeah, just don't do something like this. Just be very careful when you use any form of pointer arithmetic, pretty much.
Just use other functions that are pre-made.
Exactly. Okay, off by 1 errors. These are pretty much like buffer overflows again. Just a bit more harder to find, maybe. They can be caused very easily by miscalculating the length of an array or string. So first of all, why would you care if it's only a 1 byte? So off by 1 errors are 1 byte overflows we're talking about. So what can you do with that? Why would we even care? Like you go to a company and say, oh yeah, I found a 1 byte buffer overflow in your function here. Please invest time and money and fix this. They're going to tell you to get lost. Like they're not going to care. But it does actually have security implications. So say that it's like stored somewhere where the next value is some pointer. And you can overwrite one of the values of the pointer and potentially corrupt, and potentially like redirect program execution to something that may benefit an attacker. Or on the stack, you could overwrite the least significant byte of the frame pointer and thus move the entire stack frame to a location where you have enough control over it to overwrite the return address. And that's like a very exploitable bug potentially. Or on the heap, where you can overwrite heap metadata, where a single null byte overflow on the heap can be an exploitable bug, which we're actually going to talk about in the heap section at the end of the course. Should be interesting. Okay, let's look at some examples of how easy it is to happen. So here we declare a character array size 32, and then while I is smaller than equal to the size of the destination, which is 32, we do this copy. So in this case, the issue is because this uses smaller than equal. So this is going to overwrite 1 byte. This is like something that's very seldom to make. Honestly, if you get some experience, probably less so, but this can occur and does occur pretty frequently. The other example is a lot harder to spot. So you declare a buffer and you have a user. So this function takes a user pointer, which presumably points to a string. And then it checks if the string length of user is bigger than the size of the buffer. If it is, it just exits. If it's not, it copies the user, the string copies everything from user into buff. The issue with this, though, is that string length does not count the null byte when it does its length calculations. String copy, however, does copy over the null byte. So suddenly you're left with a 1 byte null overflow in this seemingly secure function. That does actually do bounds checking, but just has an issue in it. Any questions on this?
So similarly, if you were to use string and copy, str and copy, you then have to look up whether you're copying the null byte essentially, right? Because you might
or
forget
just-
to copy it,
yeah.
and you have sort of a different problem off by one.
Mhm.
Right?
Or just usually either allocate one more than you would need. Potentially just, that's like, you don't lose much by allocating one extra byte, but it does save you from like from these errors that are hard to find sometimes.
Right.
It's like just good practice sometimes, in my opinion at least, but yeah, people don't like to do it because it looks weird. Some other vulnerabilities, yes?
It's whether a function takes account of the null byte like part of a manual, or just people just happen to know.
Here the character pointer, so here we pass in the character pointer. The character pointer is going to point to memory basically as long as, it's just to some arbitrary location of memory. Just string copy is going to copy until a null byte. So here string length is similar. It's also an operation that's meant to be done on strings. So these two operations both just expect a string. If there's no, like if that's just 5,000 bytes of FFFF, the size is going to be 5,000. It's just going to fail anyways. This is like specifically a function to operate on strings in this case. Anything else? Okay. Some other vulnerabilities that we are not going to really cover today. Heap vulnerabilities, such as use after freeze, double freeze, or heap overflows. We're going to talk about these more in the second part of the course when we talk about heap stuff. Race conditions, I assume you've heard of that in 230. When two threads try to write to the same location or read from the same location at the same time and no atomics or mutex are used, some nasty bugs can happen there. Type confusions. We're not really going to care about these in this course at all, but for example, in browser just-in-time compilers, they're very, very relevant. You basically, the compiler expects an object, but you give it a float and suddenly everything breaks. And some other general programming mistakes that you will often see and what you should probably be aware of. For example, the size of macro on a pointer just returns 4 or 8 and not the actual size of the object, which a programmer might expect. The modulo operator on a negative value returns a negative result, so that could mess up all your hash tables or whatever. And yeah, also various easy mistakes doing any bit shifts. To pay proper attention to those as well. Yeah, we're not going to talk much about these anymore, at least for now. Let's just move on. Some auditing tips. So a lot of these bugs, as you may have noticed by now, can be very hard to spot, especially when it comes to integer over and underflows when they're more complicated. When the variable might have been defined 5 functions earlier and has gone through 5 type conversions, and you need to check if it's valid at this point. It can be very hard to find. So oftentimes you want to write yourself simple test programs that mimic the situation that you're like seeing in this larger target. Then just see if you can maybe trigger a bug, do something unexpected there. So another one is like pay special attention to all operations involving reading or writing to buffers, such as fgets, read, all of these. Like whenever you do something with a buffer, be careful that it can only read up to the size of the buffer. Some of like comparisons, there's like a lot that can happen there if different types are compared against each other. Yes, it's like some stuff we covered. It's like the integer promotions. Another one that we didn't really talk about is precedence and complicated expressions that do not have parentheses. A developer might assume that it doesn't need there, but he miscalculated the precedence of how it's used or how C makes use of precedence, and that could cause bugs. Something very dumb, but that can occur. Pay attention to code indentation and possible typos and missing brackets or symbols. That can lead. Precedence is a weird thing. If you need precedence, always do things properly in order. Okay, so now here's something for you guys. 5 vulnerabilities. Actually 4 and 1 bad programming practices. So look for 4 vulnerabilities. If you find one, raise your hand. It's a very, very bad program. I just wanted to fit a bunch of vulnerabilities in a few lines. Yes?
Okay, first is gets on line 19.
Yep, there you have a buffer overflow. Yes?
You're calling printf on user input directly.
That's a format string vulnerability?
Yep.
Length is undeclared in line 6, run unsigned.
Sorry, what?
Length on line 6.
Mm-hmm.
It's not a given value.
On line 6, it's the scanf. Yes. Yes?
Couldn't you, like, when you use choice, if you have the set equal to free it, and that would, like,
Here.
Yeah, in the choice switch case,
Mm-hmm.
and then you free, and then wouldn't you like probably use that for free?
Yep. You could also cause double free if you just call free again in the same pointer in the next iteration. Plenty of heap bugs in there in that small snippet of code. Yes?
Isn't string copy and buffer going to overflow because it's a max buffer, like max size?
Size
In line 7?
Line 7? No, the buffer has a size of max buff, which is 64, and the string copy has a size of 12, so it just copies the hello world string over into, which is plenty of size for that. One programming mistake is nothing here is error checked, which is kind of the fifth vulnerability, which can lead to unexpected results. All of these printf calls, whatever, or gets calls at least, should be error checked. One more vulnerability in this though. Yes?
Potential used after free or double free in the switch case.
Yep, there are plenty of heap vulnerabilities in there. We hadn't mentioned that, but yeah, there's a lot that can have to go wrong here. That's you using a while loop and doing whatever the user tells you to do. That's completely wrong. Yes?
Is it considered bad practice not have a default case in the switch?
Probably, yes.
Yeah.
Everything in this is bad practice.
I don't think it's involved.
I just wanted to have the minimum lines possible for the maximum amount of bugs. Yes?
Is it possible that you get a really big length value and then plus 12 it'll overflow?
Yep, that's the final bug. If you give it a very large length value, the length plus 12 is going to cause an overflow, and suddenly it's not above max buff. And then here you read length as a really large value and copy it all over into buff. Have a buffer overflow. Cool. Any questions on these? Nice. You guys did a lot better than my binary exploitation workshop last semester.
You covered
The only, no, not really. Just if you free a buffer and then attempt to use it after it's being freed. And we're going to talk more about those in the heap section. Just it's going to take a while to go into like why that's an issue. Yeah, during the binary exploitation workshop, the only one that found any issues in this was Professor Marius Mineo. The entire rest of the workshop had no input on it.
As you would expect.
Okay, so let's talk about the cost of fixing vulnerabilities. Why do vendors not want to fix them? So yeah, they might often say, they're not serious issues. We don't want to invest money into it. Like a security research at a company is probably going to cost them $250,000 to $800,000 per year. They don't want to spend that money. So they might say, yeah, ASLR is a thing now, this mitigation is a thing, buffer overflow is not exploitable anymore. Why should we care? Well, they are. And pretty much history has shown where there's a will, there's a way. Hacks are always going to get in. All bugs are potentially exploitable until proven otherwise. So in this class, we teach exploit development. As a security researcher, why would you care? Let's say you want to be completely ethical. Why would you even want exploits? You can just find the bug, tell the company, hey, I found the bug. The company's usually not going to care much, though, unless you can show them that you can at least cause crashes in their software, even better if you can actually exploit it. Which is, if we have time, I'm going to look at an exploit in a bit. That was produced recently and got a $50,000 reward by a CTF team consisting of mostly high schoolers and college students. So just like some extra references, if you want to look at them, 2 very good books. The purple one may be a bit outdated. The other one is very, very good. In my opinion, the best book on the subject out there by far. Covers vulnerabilities like web, memory corruption, auditing practices. Very good book if that's a subject you're interested in. Definitely not necessary for the course, not a textbook for this. If you want, though, very interesting read in my opinion. Okay.
Something real quick. Did anyone go to the Akamai talk the other day? The security talk? Alright. So we've been talking about like all these bugs and possible exploits. Even just like crashing a program is good enough. So if we do like all these buffer overflows, you can crash a program pretty easily by just corrupting memory. You might think, okay, sure, I can crash it, but I can't do anything bad. That's still like very important because if you take down Amazon servers, they're losing how many millions every hour. And often people run attacks that crash programs and do stuff in the background, and it's kind of just like a distraction. So if you came to the Akamai talk, an example would be often whenever banks are attacked and services are taken down, there's usually someone inside the network trying to do something while like everyone's focused on bringing back the website. So you got to think like, what is the reasoning for attacks like these? Is there an alternative motive or something?
Okay, all right. I said we weren't going to really look at tools, but here's something very quickly. This is a real vulnerability found in that me and a friend of mine found an IoT camera 2 months ago, approximately.
Can you make the font a little bit bigger?
Yes.
Thank you.
Can I?
This is just a fancier Udra.
Yeah, I'm not sure if I can actually. Sorry.
Is this Spinja?
Yes.
Yeah.
Okay. This is the line we care about. I'm just going to explain it real quick. So this was an IoT camera we found about 2 months ago. Camera has a couple million users by a US company, fairly major software you could say. And here's a logging function. This logging function, you look at the, so it's like something that has like the reference of this function where it's been called. Don't know if this is readable, but it's been called over 1,000 times in this program. It's a very major function. It's not like some small function that was written in a day and never used. This is a very major part of this camera. And it's a logging function. And don't want to go too deep into it because we have something else that we want to go over as well. But here in the very end of the function, it calls printf on a buffer that we as the user can control. So there's a format string vulnerability that you can use to crash the camera and get remote code execution on it. The camera vendors didn't care, never even got back to me, but yeah. That's like, you say like printf format string, who's going to make that mistake? It's so obvious, but there it is.
Literally, the compiler will warn you.
Yep.
Actually, on certain Linux distributions, the compiler will refuse to compile your code if you do that.
Yep.
Just an interesting question. What is an IoT camera?
Just like some embedded device, just like some camera, some like some web, it's like some camera that you can like put on your wall and connect to from your phone, for example. Yes.
Which IoT camera?
I'm not going to mention that here because.
Just so we know not to buy it.
All of them are just as bad. This one. Very fair. I bought this one because it was the most popular one, and from a US-based company. So
we know it. Devices are awful.
Yeah. Okay. So went through some vulnerabilities. Let's just look at some other real project and find the 0 day. GitHub wants to load.
I volunteer my crap code from high school, but it might still be too good for this.
I guarantee everyone here has written a bad secret project.
So let's look at zip parser written in. So I just looked up the zip parser. We go for C, and we choose this random zip parser project that has 1 star. No one's ever going to use. If we find a bug in it, no one's going to care.
And also, like, who writes a zip parser?
Exactly. That thing is
like,
completely useless.
You only ever do that for fun. I'm sorry.
Okay. Let's get the project. Okay. Let's see. So we have a few files, not very many. Can assume that. Let's see. They provide us a sample zip file. Usually, you probably shouldn't run without actually looking at the software, but we're in a VM. We don't care. Exec format error. Okay, so we look at the zip file. Okay, it's not compiled for x86, it looks like. Let's look at the makefile first. Okay, looks fairly forward. Let's just add compile flag -g, get some debug symbols in there, and let's see if we can compile it. Okay, we got lucky, compiled. Usually it's not going to happen that easily, but okay. Zip file cannot be none, so you specify -f apparently. Okay. Cool, it ran, it apparently just runs some tests and it's completely worthless. Okay, so we have a few files, very small project, but we still want to probably like choose a good location where we would want to start. Here it says zip file, or it has like some strings in it, probably from the main function. It's probably where it like starts execution, so let's just start looking at main. Okay, so get some arguments. Here it checks. So get ops use like parse arguments and switches on what the argument is. If it's L, it sets list flag to true. D is zip directory. F is the one we just used to specify zip file. Okay, so you can specify some arguments. It looks like here it does some basic checking if we actually like supplied one. If not, we like get the error message we got earlier and we return. Okay, so here we execute the glibc function stat on it. Stat basically just gives some information back about a file. Also error checks. At least the error checking is good here. You don't see that in every project at least. And we get the zip file length. It's done using the stat function, which is correct. This works. It's not the most efficient way to calculate file lengths, but it's fine. Then we open the zip file. Error check again. It's good. And here we mmap is basically like malloc, just that the actual implementation details are different, but for our purposes, we're just going to say we allocate space on the heap for zip file length, we make it read-only, and we, it has like some extra flags, we don't really care about them right now. So they allocate space on the heap for zip file length, okay? So it looks like they may want to load this zip file into memory and operate it on it there. Actually, they pass in the file pointer off the zip file into mmap there, which already does that for them. Okay, so let's talk about like zip file internals. There's like a bunch of different headers, like specify where you can find different files in the zip file and stuff. So here it looks like it calculates, I don't even know what this is. It calculates based on the where pzip adder, looks like that's where you have the heap allocation. It takes the zip file length offset, so at the very end, and then it subtracts some magic value from it that appears to be 22. And this is apparently PU, I have no idea what that is. Calls this function on it, and okay, so this looks like it probably checks the last few bytes of the zip file, because zip file has somewhat of a magic header at the end of the file, where, yes, look at this real quick. It runs this on this get4le, which specifies a result, and into the result it does some bit operations, and judging by the name and from what it looks like it just reads in an integer from a 4-byte location of memory. So it basically just constructs an integer. So we construct an integer out of the last few bytes of memory, and then we compare it against this, which, according to the comment, is pk56, which is one ending header of a zip file. Okay, so far they verified that it's a legit zip file. They allocated space and memory for it. Cool. Looks good so far. Looks fine. Here's some more of this where they extract, get 2le, so I assume a short. Okay. This time they do the exact same, just extract 2 bytes of memory and assign it to a short, and read it into the entry offset and entry number. It's like, again, it's like offsets from the zip file. Let's move down a bit more. Okay. Here it uses the entry offset that it extracts from the zip file here, gets a central directory. This is where a zip file has like metadata in it to specify where files are located inside the zip file pretty much. Creates a hash table. Has some heap stuff in it. If it's null, it just frees it, and then it mallocs over it again. If it's null, it frees it. See if we can arbitrarily call the destroy function. Okay, it looks like it's called here, and better. So look at the references. Looks like it's called from zip.c and from hashtable.c on line 24, or that's where it's declared, and then zip.c on line 423 it's used. Let's look at this real quick. Looks like that's a label at the end that just destroys everything that's done, so that's assumably not something we can trigger multiple times to trigger a use after a double free bug where we free a memory region twice. Where it was. Let's actually ignore the hash table because we didn't talk much about heap bugs, so let's just move on from that for now. Although it's very possible there's a heap-related bug in there as well. Here it declares a loop to 0, loops until entry number, increments to loop, does some checking on some bytes, and then reads in a bunch of data from the file into, or from the memory where the file is mapped into variables from a struct. Okay, there's a very, very major issue here. Anyone been able to spot it? Yes?
Couldn't you just pass in something that has like a valid zip header and then like has one data that it's trying to read here?
I'm sorry, I didn't get the last part?
So it's like, it has the valid zip header, but like it doesn't have any of the data that it's reading here, so like it could draw
it does calculate a length for it, but yeah, that's on the right track. But what I'm getting at, they memory map the zip file into the process memory, then they trust the zip file to tell you how many inputs does the zip file have, and what is their size. And then here it just loops through every single one of these, and just uses this, which dereferences memory. So you can tell it that you have 500 entries in your zip file, and it's just going to keep looping through and access memory out of bounds. Yeah, it seems like a very straightforward bug. Let's say we wanted to care to exploit this. What could we do? What would your next step be? I'm out of battery almost. Yes.
Maybe like cook up like a evil zip file that has like overflows the number of like entries in it. Basically.
Yep. Exactly.
Does anyone have any questions about this stuff, or the next restructure will be actually taking advantage of buffer overflows and exploiting them?
It also seems to assume the structure of a zip file. It just like.
I mean, the structure is specified. So if it's a valid zip file, it's going to be fine. Okay, so we discussed an attacker could do some weird stuff here, specify invalid zip files that are not going to work. Okay, and it's completely died. Okay, so judging from this, the zip file, it reads in arbitrary data, it dereferences it. You could build an arbitrary zip file and you could crash the process very, very easily. If you would keep looking through it, you'd probably, given how it's written, find a lot more bugs of that nature. You'd probably be able to write an exploit, and there you go, you have a 0 day. Okay, any questions on anything this lecture? Yes?
How did you manage to get that source code from the IoT camera?
They had their firmware uploaded, so that wasn't source code, that was the binary reverse engineered. So they had their firmware public, although you could also just buy the camera, take it apart, desolder the chip, load the software into your computer and work off it like that. But they actually had their firmware public, so we could just download it and extract the operating system, the file system, and the various things of it, and work on that.
So is the problem of the
Not going to take very long. I'm just going to quickly finish up what we were doing last lecture. So just a quick recap. We just like for the vulnerability that we were looking at the time, it mallocs some space for the zip file that it reads in, and then it performs multiple operations on the zip file where it dereferences various offsets that you can give it via a zip file. So it just trusts attacker input and does stuff with it. So we're not going to talk about how to exploit it today, but just so someone mentioned, I think last time I asked if someone had any ideas on how an attacker might go about exploiting it. I believe someone said that it could pass a corrupted zip file to here, so let's maybe look into that. In this case, actually, let's talk about before we do that, let's talk about a different way of finding vulnerabilities for a second. So last time we went over source code review, we manually read through the code and we found this issue that might be a potential security vulnerability. It's definitely a bug though. So what is maybe like some more efficient way that one could go about this for larger code bases, like browsers, for example, have millions of lines of code. There's so many vulnerabilities found through source code review, but there's also another way that is very popular, and it's called fuzzing. This is basically where you send pseudo-random input to a program and hope something crashes it. So in this case, we said that we reviewed the source code and we think that there's a bug here. We could manually create a zip file that has corrupted headers and see if we can trigger the bug. Or since it's a very straightforward bug in this case, we could also just run a fuzzer into it and see if the fuzzer can find it as well. We're only going to cover fuzzers very briefly in this lecture. You don't have to know much about it. It's just an introduction into a different way of finding vulnerabilities. We're going to talk about it in a lot more in the very last lecture of the course, so at the end of the year, where we talk about what modern fuzzers do. In this case, this is the directory, this is the zip parser we're looking at. Okay, so this is the fuzzer we're going to be using. It's a very small 80-line fuzzer written in Rust. So in this case, it starts by reading in the input, which gets from, so in this files directory, so if we look at the files directory real quick, this is the default zip file. It's a standard zip file that that's the one that was given by the GitHub repo we downloaded. So this is a default zip file, works perfectly fine, doesn't have any issues in it. And that's going to be our initial starting point. So the fuzzer reads in all the files from the files directory at the beginning, which in this case is just the minis or minzip.zip file. And then for all the threads, I guess let's reduce that a little. And then it spawns 8 different threads, and for each thread it spawns a worker that runs the thread, that spawns like different, so for every thread it spawns the worker function, and then below is just in the main thread it runs some fuzzing statistics that it prints out to us. Yeah.
What is that notation of for thread ID in 0.8?
It's just Rust for loops, basically like for Python for I in range 8, kind of. Okay, if you look at the worker function, this function is spawned for every thread, and we pass it its unique thread ID, which is just 0 to number of threads, every thread has its own ID. The corpus, this is the files, the initial files, which in this case is just the minzip file, read into memory at this point into basically an arrays of U8 bytes. So basically just an array of files, and each of the files is just represented as another array of bytes. Basically just like the easiest form one could represent that. And hex just a messenger that's like used to pass messages between the threads, and in this case the fuzzing statistics. And then this is the main loop. In it, it goes through, it basically just takes one of the inputs at random from the corpus. We only have one, so it's always going to be the same. Gets the length. And then it just swaps out completely random. This is absolutely horrible how this is done. There are much better ways to do this, but this is the simplest way possible. It takes 0 to 8 random bytes in this file and replaces them with a completely random byte. So basically just takes this totally valid zip file, corrupts some random bytes in it. That's all it does pretty much. And then it calls the fuzz function with this now changed or mutated zip file. And the fuzz function basically just runs the zip parser and passes this new file as an argument. And then it checks what the output is. If it wasn't, the output was -11, which is the output for a segmentation fault. It saves the input that caused the crash. So basically, it runs the program, or it takes in files, it mutates random bytes, it runs the program with it, and then it repeats. If it's a crash, it saves the input. Any questions on this so far? Yes.
What language is it?
Rust.
Oh, got it. Thank you.
Any other? Like the length is not relevant. You don't need to understand how exactly this works. Just like wanted to quickly go through the source, like explain the theory behind it. Yes.
Maybe you should say what a U8 is.
Just an unsigned 8-bit or just a byte. Anything else? Yes.
Maybe this is a little too into fuzzer specifically, but how do you extract any meaningful information out of the results? So here we're changing a random 8 bytes in a zip file.
Yes.
What does that tell us about how the program's crashing?
In this case, we just get that the program is crashing. So here in this line, it checks the return code of the program. If it's a segmentation fault, you save the input that caused the crash. There are ways to automate like some of this analysis, which crashes are useful actually. But in the end, most comes down to you save the crashes, and then you manually inspect them afterwards and see what actually caused the crash.
Okay, so it's sort of up to the user to figure out, okay,
yes,
we crashed and here's why.
Yes, exactly. Anything else? Yes?
Does it save the line where it crashed?
In this case, no, but that's certainly possible with better fuzzers. This is just as simple as it gets, pretty much for example purposes. Okay. Okay, so here we just specify the file the binary we want to run, which in this case is zip binary, minus f flag, and we give it the file. So let's just run it. Okay. So the first column here of the output is the current time, so we're in 5 seconds to fuzzing. These are the cases it's run so far, which is 8,000 approximately at this point, 10,000 now. The fuzz case per second, so how often it's running the program per second, which in this case is about 900 times on average. And the crashes. Looks like we've already crashed it 70 times. So it looks like we've had 22,000 fuzz cases, crashed it 90 times. That's a pretty good rate of crashing it. Means it's probably pretty vulnerable. This is, in this case, a very small scale example running on Google, for example, they fuzz their Chrome browser with 24/7 with about 4,000 cores. So at that, even on a single core machine, if you optimize it across cores, on like a personal machine, I built a fuzzer, or I am building one for independent study right now, and it's getting around 3 million fuzz cases per second on 16 cores. So you can scale that very heavily if you put the effort into it, and that's a big part of fuzzers. Okay, so we have some crashes. Now, in this case, this is written terribly, so it's only saving one case per thread, which is fine for our example here, because it doesn't like create any type of unique random hash. So like it needs to actually save the files that caused the crash. And since I didn't like want to do anything pertaining to randomness to create the files, that every thread can just save one file pertaining to its unique thread ID, which is not what you want to do, but we have 10 crashes or 12 crashes here, which are enough for our purposes right now. So. Okay, so let's open up GDB. Get the, so right now we're in Pwn debug. You all know it by now, I hope. And we're in the zip binary. So let's see if we can manually reproduce one of the crashes. So we go to the crash directory and we just choose one of them, temp2.zip, run it. Okay, and we crashed in the get2le function. That was one of the functions that we talked about that would dereference one of the inputs we gave it. At this point, we probably want to know. So we have a crash. It is what we expected. Maybe we can, in GDB also, at the bottom you see backtraces here. So we can go back a backtrace to F1 to go to the main trace. And if we look at the context here, we can see we specifically crashed on the get 2 little endian bytes of the offset. So it looks like that's what caused our crash in this case. So if you're using a fuzzer, often you're not going to have source code or debug symbols, so you're not going to get that pretty view, so you're going to have to follow the backtrace and understand the code with a pure assembly. In this case, we have the source code, makes it nice and easy, and that's our first crash. Let's look at a couple more. Let's look at the first one. It looks like the exact same. Okay, so it looks like they're all in the exact same place, but we suspected that there are a lot more vulnerabilities. I think the get 4 little endian bytes is just as vulnerable. So the fuzzer is always crashing on this thing right now, which is an issue for us because we want to find all the bugs in the program, and this is the easiest crash to get, so it looks like it's always going to be crashing at the exact same point. Does anyone have any ideas how one could fix this, that the fuzzer can potentially find more bugs than just this one? Yes?
Once it finds one set of byte it was changing to cause the bug, it stops there, and from there on it doesn't switch those bytes.
Yes, so basically making your fuzzer smart. It's actually a lot harder than it sounds, especially for an automated. So you need to do something called taint tracking, where you do tracking of what the inputs actually edit, and then change your fuzzer corpus generation based on that. Yes, that is one option. That basically, it's a very valid option. It requires you to write a much better fuzzer, though. That's usually target specific as well. Yes. Yeah.
We can just fix the original code, or we can't fix it, we just NOP it.
Yep, that's the easier. That's, in this case, we have source code. It's very easy. We fix the bug in the source code, this specific bug, then we can recompile it, keep the fuzzer running, and look for more bugs. Okay, so that's pretty much all we had on this so far. For the quick question on smarter fuzzers, so this is a very naive fuzzer. It does nothing interesting. It just runs it with basically randomly mutated inputs. Fuzzers can get a lot more complicated. There have been many years of research have gone into them. It's a pretty common PhD program for security researchers. So fuzzers can get very complicated. There's a lot of more advanced techniques behind them. We're not going to talk about them today. We are going to talk about them at the end of the class. So this is a very useful vulnerability discovery technique. Less so for the projects in this class. For those you will want to rely on reverse engineering and source code analysis just because of how they're laid out. But yeah, any questions on fuzzing?
So, I mean, just because you crash doesn't mean you have a vulnerability, but you're saying it's sort of like a crack in the door that maybe this crashed because it's writing too much data based on the encode, for example.
At that point, you want to then load it into a debugger, follow the back traces, and see what actually caused the crash, and note down if it might be a potential vulnerability or not.
Okay.
But in practice, very many of at least bugs that like cause like either buffer overflows or any like heap-based bugs or race conditions, a lot is exploitable if you have the skills to do it.
Okay.